let me just remind you where we got to last time. I wrote down the action for a particle and I wrote it this way because, well, of course, we could have introduced some parameter like that, but this expression doesn't depend on what that parameter is because the square root of these two d lambdas cancels that guy. So that's the expression for the action for a point particle. And then what I argued is it's very natural to contemplate changing this eta to a g mu, which is a function of x. And if you remember what eta is, and this was what Minkowski taught us, that eta is the quantity you use to measure lengths on space-time. And so likewise, g mu nu, that's why it's called a metric. It's used to define lengths on space-time. And so the idea is that g mu nu could be any function of x. And as we'll see in a little while, what that means is you're describing a curved space-time, whereas this is a flat space-time. And we're going to define curvature and so on, and this will be the key to Einstein's equations. So the correspondence is going to be, so we went from special relativity, where we had lambda and lambda twiddle. You remember that lambda was the coordinate transformation for upstairs indices, and lambda twiddle for downstairs indices. So this is special relativity. And of course, we have this metric eta. And in general relativity, we're going to have, instead of lambda and lambda twiddle, we're going to have the coordinate transformation matrices, dx prime dx and dx dx prime. And it's a fact from partial differentiation that dx prime alpha dx mu is the inverse matrix of dx mu dx prime beta. Okay, just by using the chain rule, that if x depends on x prime, then if I differentiate, if x prime is any function of x, then if I differentiate dx prime alpha with dx prime beta, obviously this is delta alpha beta because dt dx is 0 for partial derivatives, dt dt is 1. So this statement is just the chain rule plus partial differentiation plus this. So dx prime alpha dx prime beta is equal to dx prime alpha dx mu dx prime beta by the chain rule. So these matrices, coordinate transformation matrices, obey exactly the same equations the lambda obeyed. And so everything we did with tensors in special relativity goes straight over to general relativity, with the exception that the metric is not unchanged. Okay, that the metric in a new coordinate system would be changed like a tensor. Okay, the metric with 2, and this is now considered as a function of x prime and g of x. So the metric in the new coordinate system is given by this tensor transformation law from the metric in the old coordinate system. What is invariant is the line element. dl squared, which is g mu nu dx mu dx nu, and then that's equal to, as you can see from this formula, that's equal to g prime mu nu dx prime mu dx prime nu. So the line element is invariant under general coordinate transformations. Okay, and again, when I replace eta with g, the action for a point particle is just the length of the world line as measured with the metric g. Now we're going to show that in the vicinity of any space-time point, we can always choose coordinates in which g mu nu equals eta mu nu at that point. Okay, so you've got this huge freedom to choose coordinates, x prime of x, and you can always use it so that at a point, the metric is just the Minkowski metric, eta mu nu. And the picture you should have in mind is that we've got some curved space here, and we've got some point P, and in the vicinity of P, the geometry looks flat. Okay, so obviously if you take a big curved surface and you look very close with a microscope, it's going to look flat, and in fact that's exactly what this represents. And now we can state one of the fundamental principles of general relativity. And this was Einstein's great insight. And he tells the story where he was sitting in his chair in his office, and he's in the patent office in Switzerland, I guess, or maybe by then he was in some university or other. But he was sitting in his chair, I think it was in the patent office, he was sitting in his chair, and suddenly he realized that if somebody was accelerating the chair upwards, as if it were in a lift or something, he could not distinguish that fact from the fact that gravity was pulling him down. Okay? And the advantage of the former point of view is that any body that was being accelerated upwards in a lift or by a rocket would feel exactly the same force, or feel exactly the same, would experience exactly the same acceleration. Obviously, they're all being accelerated the same way. And so this immediately would explain why gravity couples to objects of any mass in the identical way. So in Newton's equation, there was this puzzle why the mass, the gravitational mass, the gravitational force, for example, was g, let's say the mass of the Earth, the mass of the object, times r, Newton's gravitational force. The puzzle was, why is this mass exactly the same as that mass? Why is the gravitational force exactly proportional to the mass? So what Einstein realized is that maybe gravity is actually the consequence of something universal, that everything is forced to see the same gravitational acceleration. Acceleration is completely independent of the mass. Everyone sees the same acceleration because acceleration is actually due to the fact they're all living in the same space-time, and they see the same curvature of space-time. So the equivalence principle states the following. In the vicinity of every observer, and and I'm going to, well, let's start off with every point in space-time, and I'll generalize it a little bit. And now we get the physics. So the key clause is that the laws of physics in the right coordinate system don't involve gravity at all. Yeah.
I see why the general relativity would show that those little m's would be the same as the inertial and gravitational mass, but I'm curious from the old perspective, what was the reason that the big M would be the same as the source object's inertial mass?
Well, you've got this. Any object sitting on the Earth's surface feels the gravitational field of the Earth. So the Earth bends space-time, and any object I put in its field will, no matter what the mass of the object, will feel the same acceleration.
I guess I mean it seems like there's another sort of coincidence, which is that big M, which is sourcing the gravitational field, is the same as the Earth's inertial mass.
You could say that, but the cancellation is between these masses, not between big M.
Oh, I know. Okay.
Yeah.
I think that would follow from the third law, right?
Gravity does respond to mass. When we do Einstein's equations, we'll see that the bending of space-time depends on the density of matter. So, in a way, what this is saying, let me see. You see, what this is really saying is that, as far as gravity is concerned, inertial mass is not a useful concept. There's no such thing as inertial mass. Everybody's in the same space-time, and they move according to the space-time. So a short way of saying this is that, i.e., gravity is the bending of space-time. Okay, and since everybody lives in the same space-time, they see the same gravity, same effect of gravity. They're all following world lines, and their world lines accelerate, and the acceleration is the same for everyone because they're all seeing the same space-time. Yeah. I do mean unaccelerated.
Unaccelerated?
I do mean unaccelerated. So if Einstein's sitting in his chair, okay, he's trying to distinguish between a physical situation in which gravity is pulling him down. There's some force of gravity pulling him onto the chair. The other possibility is the chair is pushing him up, right? And so what he's saying is that if I picked a coordinate system which was freely falling, okay, so if I just let somebody go, so they're next to me and I let them go, there are no forces acting, and there is no gravity, well, they're just falling through space-time. So if they're falling through space-time, they'll look at me and they'll say, oh, the chair is accelerating you. Okay, so you can't distinguish between a force of gravity pulling you down and the chair pushing you up. And in the locally inertial frame, in the freely falling frame, the explanation for what's happening is there is no gravity, but the chair is accelerating you. Yeah.
I just wanted to add to something that Daniel was saying, because I actually thought that was kind of interesting. I agree that in this equation, the inertial masses cancel, and we just have the big M, and that's the only one, and that as far as gravity is concerned, inertial mass isn't useful.
Right.
I've never done electromagnetism or other forces in the context of general relativity, so maybe we'll get to this later in the class, but don't we still have to have an inertial mass there?
Yes, we do. Yes, we do, because they don't cancel.
Big M in this equation is the same as the inertial mass in when we have non-gravitational forces?
I guess so. I mean, so in electromagnetism, obviously we have a formula. You know, if the Earth was being accelerated by an electric field, you know, this would be the mass of the Earth,
right,
if Q is its charge. So you may feel puzzled, you know, why is this mass the same as the mass that caused the bending of space-time? Yeah, it's an interesting question. I don't know. Let me take a shot at it. That mass, certainly the origin of it, well, yeah, maybe that's true. You see, this mass, you know, this whole formula, what does it really come from? It comes from the momentum of the Earth. Where does the momentum come from? It comes from the stress tensor. Okay, it's integral d3x of the energy momentum tensor. Okay, now the stress tensor of the Earth, which includes its energy and momentum, is exactly what causes the curvature of space-time. So according to the Einstein equations will be the curvature of space-time is proportional to the stress tensor. Okay, so according to Einstein, these things are strongly related. And so if you believe that the stress tensor is proportional to the mass, which is pretty clear, then it's totally plausible the curvature is proportional to the mass. And so I think Einstein's equation explains that correspondence.
Can you say again why the stress tensor is proportional to the mass on the right part of the picture?
Yes, because what we showed before was the energy momentum in the electromagnetic field was d3x t naught I. Okay, so I introduced this idea of the stress energy in the electromagnetic field, and then the momentum in the electric field was the integral of this quantity. And the energy was also the integral of this quantity. Now, the Earth is not an electromagnetic field, but it's an object. It has a stress energy tensor. And in exactly the same way, the momentum, this guy here is really d by dt of the momentum of the Earth. And the momentum of the Earth is going to be related to its stress energy tensor. That stress tensor is the source of curvature of space-time. So I think Einstein's theory does explain why this mass and that mass are actually the same. Okay, so this is the idea that gravity is the bending of space-time, and I haven't given you any geometrical pictures. I've just said that the way you measure length in space-time is through this metric. It can be a function of x, and as we will see in a moment, the curvature of space-time is related to g mu nu of x. Yeah.
In the tutorial, we had a stress energy tensor, like for mechanical and also for electromagnetic things. Is there like a way to reconcile? Like, how do I know? I don't know.
We've only done some examples so far of stress energy tensors. Next week, we'll give you a completely general formula, okay? Well, the general formula is that the stress energy tensor is equal to 2 over root minus g of the variation of the action with respect to the metric. Okay? So you'll see why this happens. And essentially, this happens because the Einstein equations follow from the action, when you follow from varying the action with respect to the metric. So this is the nice formula for the stress energy tensor. As I mentioned, if I use Noether's derivation of the stress tensor in electromagnetism, it's actually quite messy because you have to add boundary terms and it all gets rather complicated. But there's this shorter derivation which comes about when you know about gravity. And you know, that's the easy one to use. Okay, so let us now prove this. Let's now try to prove this fact that it is possible to choose coordinates in which the metric is flat at, i.e. equal to eta. The metric equals eta at any point in space-time. And actually, we can do better than that. We can also choose coordinates such that the first derivative of the metric is 0 at any point in space-time. So the metric is going to be eta. And if I think of Taylor expanding the metric around some point, the term proportional to x will also, we can choose coordinates, so it's 0. So let's see how we do that. So locally flat coordinates. So we'll start from this formula, g prime mu nu of x prime. So that's our metric in the new coordinate system. This is equal to the metric in the old coordinate system times dx alpha dx beta dx prime mu dx prime nu. And let us assume that we're given some metric, g alpha beta of x. So what I'm going to do, just for convenience, I'm going to choose the point x equals 0. So I'm some point, P. I've got these two coordinate systems, which I can think of as let's see, a grid, okay? So these are the x coordinate systems. This is the x coordinate system. This is the x prime coordinate system. Maybe I should do it in a different color. So every point is labeled by x or x prime. Here's the x system. And this is the x prime system. They can bend respect to each other. Can do anything. And then I've got some point P. And for convenience, I'm going to choose P to be at x equals x prime equals 0, just to make the algebra shorter. That could be a constant. It won't affect anything. So G alpha beta of x is G alpha beta of 0. That means the metric at the point P, which has coordinate 0. And then it'll have a Taylor series, x lambda. Okay, so Taylor's theorem says if you have any function of x and you expand it around some point, it works even for functions of many variables. When you expand it around a point, then the function is given by the first derivative of this function at that point. So this is equal to G alpha beta comma lambda evaluated at 0. But it's a constant. Okay, the derivatives of the function are just a constant at that point. And then we have a half b alpha beta comma lambda sigma. This again is d2 g alpha beta dx lambda dx sigma evaluated at the point 0 times x lambda x sigma plus dot dot dot. Okay, so the original metric I can Taylor expand around this point, just because it's a function of the coordinates. What we're going to do is we will choose the following transformation between x and x prime. Okay, so the idea is that I have a formula for x prime of x, and I can invert that formula, x prime of x, and I also have a formula x of x prime. Okay, you can map between these two coordinates. It should be 1 to 1, and basically the condition for it to be 1 to 1 locally is that that matrix dx prime dx should be invertible. Okay, so that's the assumption. And we're going to choose our x prime. X can be any function of x prime, which is locally invertible. 1 to 1 means invertible. X k alpha gamma x prime gamma plus 1/2 L alpha gamma delta x prime gamma x prime delta plus 1/6 m alpha gamma delta epsilon x prime gamma x prime delta x prime epsilon. Okay, and again, these constant here are just the derivatives of this function evaluated at the point. Okay, so I've got x of x prime, and so for example, k alpha gamma equals dx prime alpha gamma evaluated at x prime equals 0. Plus dot dot dot. Okay, is that clear? So I've got some metric, it's some random function of x, but I'm going to assume I can differentiate it. I'm going to assume therefore it has a Taylor series. So it has a value at 0. This is the expansion, and this is the Taylor series. And then I'm going to say, well, I have this freedom to define x of x prime, okay, or x prime of x. And the entire freedom is encoded in these constants, which are the derivatives of x with respect to x prime. So this is the second derivative, right? L alpha gamma delta is equal to d2x dx prime gamma dx prime delta at x prime equals 0, right, etc. Now, the question is, these are completely free parameters. Can I choose these parameters in order that this metric is equal to eta at the point x equals x prime equals 0. And furthermore, you see I've got lots of parameters. How can I use these parameters to make this metric as close as possible to eta? Okay. So question. How can I choose these constants k, l, m, ... to make g prime mu nu of x prime as close as possible to eta mu nu? Okay, that's what I want to do. I want to choose coordinates in which space-time looks as nearly as possible equal to Minkowski space-time. So the answer is very easy. We just calculate g mu nu. We'll begin by doing that. So let's calculate g prime mu nu at the point 0. X prime equals 0. So g mu nu at x prime equals 0 is obviously g mu nu at x equals 0, which is this expression. So this is g alpha beta at 0. And then I've got to work out those dx dx prime matrices at 0. So work out all of this at x equals 0. Dx dx prime, I get this matrix. So I get k alpha mu, k beta nu. Okay, and I would like this to equal, can I choose this equal to eta mu nu? Okay, so the answer is yes, because I can always write this as, if we write it in matrix notation, you see this is the matrix G multiplied by the matrix K. So this expression is just K transpose G of 0 K. G of 0 is a symmetric 4x4 matrix. Can I diagonalize such a matrix with a similarity transformation? Answer is yes. So if we choose, so basically what I'm going to do is choose K to involve an orthogonal transformation that will diagonalize G. And then I have still some more freedom in K. And I'll choose K to be a diagonal matrix that will rescale all the all the eigenvalues of G, rescale them all to be 1 or minus 1. So if we choose K to be an orthogonal matrix, and L, which will be a diagonal matrix, diagonal 4x4 matrix. Okay, then since G is symmetric, G of 0 is symmetric, we can choose O so that O transpose G of 0 O is equal to a diagonal matrix, and this will be of the following form. So it's got to be diagonal. And in order for the matrix for G mu nu of x to be a legitimate metric on space-time, it must have, so we see this now, G mu nu is symmetric. It must have have one negative eigenvalue and three positive. Okay, so I was, initially I just said we replace eta by g. Now we're learning that actually if we want this equivalence principle to be true, we have to put some conditions on g. It's not a very strong condition, but the condition is that g has to have one negative eigenvalue and three positive eigenvalues. And then I can always rotate the matrix into this form, L3 squared. Okay, so one negative and three positive, and then choose L to be equal to 1 over L0, 1 over L1, 1 over L2, 1 over L3. And then what we have is that, so that G prime mu nu of 0 equals eta mu nu. Any questions about that? So I can always choose coordinates, provided G has this property, one negative, three positive eigenvalues. I can always choose coordinates so that G prime is eta at that point. Any questions? No? Okay, so let's go further. Furthermore, see, I've only used up the K. I've only used this freedom, the freedom to do linear transformations in coordinates. It's all I needed to use to set G equals eta. But I can now do quadratic transformation involving the coordinate squared, coordinate distance squared. So furthermore, it turns out we can choose the quantities L, this L, let me give its indices, it'll distinguish it from that L, L alpha gamma delta, so that G prime mu nu comma lambda equals 0. We can also, we still can play around with these L's, and it's not hard to see that you can use that freedom to set the first derivatives of the metric to be 0. So let's show that. So what is this? Is G prime mu nu comma lambda. This is d by dx prime lambda of G prime mu nu of x prime evaluated at 0. So I've got to take this formula and differentiate it with respect to x prime. Okay? So we need to calculate, so d by dx prime, of course, is equal to dx alpha dx prime lambda times d by dx alpha. And dx prime I have over here. So if I work this out at the point 0, this guy is going to turn into k alpha lambda. Okay, so when you work this out, you will get various terms. Firstly, you will get the derivative of the metric at the point 0, which is this quantity A. So you get A alpha, beta, comma, delta. And then you get k delta lambda coming from this transformation between x and x prime. You also get k's coming from these two guys. So you get k alpha mu, k beta nu. And then so that was taking the first derivative to act on this quantity. But I can also act with the first derivative on these quantities. Okay, so now I'm going to get just g at g alpha beta of 0. And this we have already set equal to eta alpha beta, okay, by choosing the k's. And then I'm going to get the derivatives acting on the coordinate transformation matrices, d by dx prime acting on this one, and then d by dx prime acting on that one. So I'm going to get two terms, which will be L alpha mu lambda k beta nu plus k alpha mu L beta nu lambda. So this is the first derivative of g prime at 0. So these L's were free. So the question is, can I choose L's to cancel the A? Okay. Now, you might recognize this. This is actually exactly the same bit of algebra we did yesterday. Okay. We've got, you see, this is invertible matrix. These are invertible matrices. So what I can do is let's see. Yes, I mean, obviously I can use this eta to lower the index on K. So what I have here is a three index object, L mu lambda. Let me see what I want to say. Yeah. So let's call the first term is m mu lambda nu, and this term is m, the same matrix, but m nu lambda mu. Okay, and it's symmetric on the first. I've just put these this L matrix over there. It's symmetric under these first two indices. Okay, symmetric on first. So M, this matrix M, mu lambda nu, is symmetric on the first two indices. Because L is symmetric on its two indices. Yep.
Is there missing a prime on that G in front of the parentheses?
Don't think so. It came from here.
Equal to eta then?
Good point. Yeah, sorry, you're right. I don't need to set it eta. You're right. It's not eta. Thank you. It's the original G. Okay, so let us just rewrite this whole expression as a sum of two matrices. It's the same matrix. You're right, this is not eta. That's the original G at 0. Okay, so what we've got, we want to set this equal to 0. So in other words, we want to find some m, mu lambda nu, such that m nu lambda mu is equal to minus a with those other factors. Alpha, beta, delta, k delta, lambda, k alpha, mu, k beta, nu. So if I can find an m satisfying this equation, then I've done it. Then I've set the first derivative of g prime equal to 0. Now, there's a kind of heuristic way of arguing this, which you'll find in Tony Z's book, which is just to count the number of parameters. So here there are a certain number of parameters. Okay, this is a matrix which is symmetric on 2 indices, and it has a third index. Okay, so the total number of components of such a matrix, if I'm in d dimensions. Okay, so far I haven't said if I'm in 4 dimensions or any number of dimensions, so let's just do it in general. If I'm in d dimensions, this would be a symmetric d by d matrix, okay, which is d plus 1 over 2 components, because you have d minus 1 over 2 components off the diagonal, right? So if you like the number in an antisymmetric tensor, you have the off-diagonal elements, and the ones above and below the diagonal are identical because it's symmetric. So you have, and then plus you have the diagonal, which is d elements. So d plus 1 over 2 is the number of components of a symmetric tensor of a symmetric d by d matrix. And then we multiplied by d, because we have d values of delta. So this is the number of number of different parameters in A. So no matter what metric I originally had, I have this much freedom in the original metric, okay, at this order in X. Now, of course, this is exactly the same as the number of components of this matrix. This matrix is symmetric on the first 2 indices, and has the third index. So the number of parameters is equal. I have as many parameters in here as I have in there, and so you'd say it's reasonable to expect that for a linear equation I should be able to solve for all those parameters. We can do a little bit better than that by using the little bit of fancy algebra we did yesterday, which is just take this equation in more detail. So the number of parameters match. Number of parameters in M are sufficient to cancel an arbitrary matrix A. The number of parameters are equal. But in more detail, you can see that you could write down that m mu nu lambda plus m nu lambda mu, and then I would add to it the equation with mu replaced by nu, and then I would subtract from it the equation with with the second and third indices interchanged, so nu replaced by lambda. And when you do all that, you will find on the left-hand side that you only have m mu nu lambda. And on the right-hand side, you have something, okay? And so you can solve for m mu nu lambda. And since you've solved for m mu nu lambda, and since this matrix and that matrix are invertible, you can determine the L. Okay, so we have proven that it is possible to choose the L's such that the first derivative of the metric is 0 in the new coordinate system. So all's going pretty well. We've reduced the metric near x to be eta to first order in x. Well, why stop there? Let's try it second order, okay? So the question is, can we choose the next set of parameters, these m's, the M alpha gamma delta epsilon so that the second derivative g mu nu comma lambda sigma of 0 equals 0, g prime. Can I choose the next freedom in coordinate transformations to make the second derivatives of the metric 0? Okay, so this was the calculation which Riemann did as a graduate student in Germany in 1830. Okay. And what do you think the answer is? Is it yes or no? It's no. So basically what it tells you is that there are too many of these second derivatives, okay, for us to cancel them using coordinate transformations. We just can't get rid of them. If this metric has a sufficiently complicated shape, there is no way to choose coordinates to second order. Well, this means the third order in coordinates, but there's no way to choose the coordinates such that the second derivatives of the metric vanish. So I'm not going to do the algebra in detail because it's messy, but I'm just going to count parameters. Yeah.
Why was Riemann studying this in the 1830s?
Riemann was studying it in the 1830s because his PhD supervisor was Gauss, and Gauss had begun to think about the curvature of surfaces. And Gauss had studied two-dimensional surfaces and understood all about the curvature of two-dimensional, so he said to Riemann, do it for any dimension. Okay. So actually we'll come back to this because there's something called the Gaussian curvature of a surface. And this is related to the embedding of a surface in a bigger space-time. So the Gaussian curvature measures how much the surface bends if you picture the surface or the geometry as being embedded in a higher dimensional space-time. But what Riemann did is he identified the quantity which describes the intrinsic curvature of the space-time, where you don't even mention the embedding. And this intrinsic curvature is related to the derivatives of the metric. This is entirely a quantity which is within the geometry. It doesn't care about how you embed the geometry in a high dimensional space. So Riemann really began to see that many aspects of geometry could be described as intrinsic to the geometry. And when Einstein wanted to describe the geometry of space-time, he didn't want to embed space-time in some other geometry. He wanted the intrinsic curvature of space-time, and that's why he had to use Riemann's construction. Okay, so as I said, I'm not going to do all the algebra to solve for M. I'm just going to count parameters. So the idea is the following. I'm going to use this expression up here. Okay, so let's write down a little bit of it. So d, we're going to say dx prime lambda dx beta dx prime sigma, and then we're going to calculate d by dx alpha d by dx beta, and then we're going to work out all of this stuff. G, and I better change those to gamma delta. So this is dx gamma dx delta dx mu dx nu. Okay, so that's the second derivative of the metric with respect to the x prime, second derivative of g prime with respect to x prime. And now everything in this expression is just a series in x. Okay, so I can plug in my g's, my g of x. I can plug in my x of x prime. I've left out the primes. Okay. This is g of x. And yes, so when I work out this quantity on G, I would do it this way, right? I differentiate with respect to x, and then I use these formulae. But this is, of course, equal to d by dx prime lambda, d by dx prime sigma. And so when I work out the action of this operator on these quantities, I'll use it in this form. Okay, because x is a function of x prime. And so when you do all that, what you're going to find is, you see, so I'm taking two derivatives of G. The two derivatives going to act on this quantity. That will give me the B matrix, okay, times K's. So basically, you will get B times K, 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 K. But when I start taking derivatives, I take two derivatives of G, I could have three derivatives on X here. And that's going to give me the M matrix. Okay, so I'm going to get things like M, and remember its index structure, gamma delta epsilon times K. And I'm also going to get A, L, K type terms where I have cross terms. So I might get something from the G. I might get something differentiating the G once. I would get an A differentiating the X twice. I would get an L. So you get a whole bunch of terms like this. Everything you know. So this is known. This is known. And we want to solve for this. Okay, by setting this whole expression equal to 0, question mark. So how many parameters do we have in this matrix M? So M, alpha, gamma, delta, epsilon is symmetric on these three indices. And so as far as these three indices are concerned, the number of independent components are just the number of components of a symmetric tensor in three indices. And it's not hard to convince yourself this is just d, d plus 1, d plus 2 over 6. Okay, so that is the number of components of a symmetric 3-index tensor. Has anyone heard of Young Tableau? Okay, so the slick way to do this is Young Tableau. Okay, Young Tableau are the way of calculating the number of components of dimensionality of the space of symmetric objects. And I'll just show you how to do it in general. So what you do is if it's symmetric, you draw the boxes this way. Every index is a box. Symmetric indices go this way. Anti-symmetric indices go down. And if it's symmetric, what you do is you put D here. Okay? You put d plus 1 there. This one is d plus 1. This is d plus 2. Okay, for a 3-index symmetric guy, there are 3 boxes. And then the answer is that you multiply the boxes and you divide by the hooks. Okay, so the hooks means you start from the left and you go this. This is 1. This hook is 2. And this hook is 3. So over hooks, which is d plus 1, d plus 2 over 6. So this hook is 2, this hook is 3. Okay, so if I give you any tensor at all, this is the answer. I'm not proving it. Okay, this is group theory. But if I give you this, and I say, how many components are there? Well, what is that? That is a 9-index tensor. Okay, it is antisymmetric under these indices, exchanging these indices. It's symmetric under exchanging them this way. And the number of components, I fill them out. So this guy is D. This one is D minus 1, D minus 2. And this would be D plus 1. This would be D. I work out all the products. I work out all the hooks. And I get the answer. Okay? I'm not proving that. You'll find this described, for example, in the book by Hammermesh on group theory. And basically, this is the basis for the theory of the symmetric group of permutations of objects. So anyway, it's not hard to check this formula for various D. So that's the number of components of these three indices, and this guy is D. So the number of components of M, number of parameters in M is D squared over 6 times D plus 1 times D plus 2. And we'd like to know, do we have enough of these parameters to cancel the second derivatives of the metric, of our original metric, which are in this matrix B. But the point is, the matrix B has a different symmetry structure. See, the matrix B is symmetric under exchange of the first two indices or the second two indices. It's not symmetric under three indices. So the number of independent parameters in B alpha, beta, lambda, sigma. Well, B is symmetric under these two indices and symmetric in those two indices. The number of components of a symmetric D by D matrix is just D plus 1 over 2. And this is the same. So if I think about this as a matrix with this many components here and this many components here, then the number of independent components is just the product. There's no symmetry between these two indices and those two indices. I can just take any one of these indices, any one pair and any one pair here. So the number of components is D squared, D plus 1 squared over 4. Okay, so this is what Riemann noticed, is that the first number of components in M is smaller than the second number in general. So the number of parameters in B which cannot be cancelled by M is the difference between these two numbers. So it's D squared, D plus 1 squared over 4 minus 1/6 D squared, D plus 1, D plus 2 And this is, let's pull the dd plus 1 out the front. So it's dd plus 1 times 1/4 d plus 1 minus 1/6 d plus 2. And so this is equal to 1/12 d squared minus 1. Okay, 1/4 minus 1/6. This is 3/12 minus 2/12, so that's 1/12. And then 1/4 minus 1/3 gives me minus 1/12. Okay, so this is the number of parameters which cannot be cancelled. Cannot be cancelled by choosing coordinates. The number of second derivatives which cannot be cancelled by number of parameters in the second derivatives cannot be cancelled by choice of coordinates. So yeah, I'll write it down here. So let's just work it out for various d. So d, the number of non-cancelable parameters in the second derivatives of g. And so if d equals 1, it's 0. So in one dimension, you can cancel all the second derivatives. Okay, in fact, in one dimension, it's easy to choose coordinates in which any metric is absolutely flat everywhere. Okay, one dimension has no curvature, and that's sort of intuitive. If I really have a one-dimensional object like a piece of string, and if I don't think about extrinsic curvature, if I think about intrinsic curvature, clearly there's nowhere for curvature to be in one dimension. Okay, in two dimensions, there's 1. d equals 2, that's 4 times 3/12, so there's 1. That means there's only one curvature in 2 dimensions. If I've got a surface, there's only one measure of the intrinsic curvature. So for example, for a sphere, okay, this curvature is positive. When I sit here, as I go away from any point, I see, for example, yeah, by many measures, you will see that, for example, the length of a circle of radius r. If I sit at the North Pole and I go out a radius r, the length of the circle is not 2 pi r. It's smaller. Okay, and as the circle gets further away, eventually it becomes the equator. And even further away, it shrinks to 0. Okay, so the behavior of the geometry is definitely not flat space, and that all of these things are signals of positive curvature. This is positive curvature. Negative curvature is where I have a hyperbolic space, like a saddle, like a horse saddle, in which this space sort of curves upwards in one direction and downwards in the other direction. This has negative curvature. A complicated case is a torus, okay, so imagine I draw this surface. How do I draw a torus? Like that. Okay, the torus, if you think about living here, you've got negative curvature because in the inside of the torus, in this direction, you're curving around like a sphere, but in this direction, you're curving the other way. Okay? But if I'm on this direction, both in both this direction and that direction, the surface is bending like a sphere. So here the curvature is positive. Here the curvature is negative. In fact, the mean curvature of a torus is 0. Okay? Which is given by Euler's number of the surface is the integral of the curvature of the surface happens to be 0 for a torus. So in 2 dimensions, there's one quantity measuring curvature. We haven't constructed this quantity. We're going to do so shortly, but we just calculated how many components this quantity should have. In 3 dimensions, there are 6. These turn out to be, so there's something called the Ricci scalar, which we'll talk about next week. It's a scalar, it's one number. And in 2 dimensions, you have one number. In 3 dimensions, you have a symmetric tensor called the Ricci tensor, which this is Ricci scalar. Ricci tensor. Okay, and then in 4 dimensions, you have 20. And this is called the Riemann tensor. And this guy is really the fundamental one, because that holds in all higher dimensions as well. And Ricci, I think, only got his name on this because he took Riemann and reduced it to these cases. It's not such a big contribution. Yes?
I don't understand why, if we took like a circle, why does that not have, I guess, a curvature in the same sense that a sphere does?
Because if you think of being an ant living on the line, okay, the question is, can I tell if my line is bending or not? Okay? And the ant living on the line really should know nothing about the outside world at all. So when they travel along the line, they should just travel along a geodesic on the line. And all that happens is they run along the line, and it's a fixed, nothing is bending, there's nothing interesting can happen. We can prove it rather easily, okay, because if I take a metric, which is any function of x in 1 dimension, times dx squared. 1 dimension, that's the metric, right? Furthermore, this function has to be positive, because we've got to have one positive eigenvalue. So I can write this as f squared. Oh, positive or negative, but I can always write it as the square of something. And then, of course, this is equal to dx prime squared if I say x prime is integral f of x dx. And so 1 dimension is obviously flat. You can choose coordinates x prime of x so that the metric is just flat. Yeah?
On that same note, if it's closed into a circle, though, you do get the possibility of like coming back to the same point.
Yes, very good.
Would be
very good question. So all of these considerations are strictly local.
Okay.
They say nothing about the global properties.
Okay.
So in differential geometry, one is only studying the local properties. When you study the topology, that's when these issues come in. Okay. So we can have spaces of you see a sort of trivial example is a torus. Let's say we're in 2 dimensions. And I can say I have a flat space, just a completely flat space. The geometry doesn't depend on boundary conditions. Local geometry doesn't depend. It's just flat. Okay? But I can identify this line with that line. What it means is that if I travel out here, I would say, okay, well, I just put myself back there, and I travel back inside the space. Okay, that's a torus. Topologically, that's a torus. It's actually this surface I wrote, because as I run around, I just come back to where I started. So the geometry is absolutely flat, but the topology is toroidal. Likewise, I would identify this surface with this surface. So as I come here, I say, by definition, I come back inside. So in physics, we say periodic boundary conditions. If you impose periodic boundary conditions, you're pretending that flat space is a torus. The geometry is flat, but the topology is totally different.
Is the geometry of that torus, that seems like it's not locally flat, right?
Yes, so in this case, so you see, yeah, so the most basic property of a space is its topology. I mean, a space is a set of points. You can define a space without any measure of distance, just by relationships between points. And so this topologically is identical to that. The second thing you do is introduce a metric. And metrically, this is not the same as that. What you are guaranteed, there's an Euler theorem which says that the Euler number, which is a number, is some normalization I can't remember, but the integral over this 2D space. So in 2D, there's a theorem that when I integrate the Ricci scalar, I have to get a certain number, okay? And the left-hand side is independent of the metric. It's a number. So when I change the metric, I cannot change this number. And so in both cases, in this case, you'll get 0 because it's flat, and R is 0. In this case, you'll get 0 because some is positive and some is negative. So theorems like this relate the topology to the curvature. But it's never local. You've got to integrate the whole curvature, then you get a topological formula. So, yeah.
You can do that. I've seen the Euler characteristic defined in terms of just dividing up the triangles and counting.
Yes, exactly.
How are those two equivalent?
They are. So there are many wonderful relations between local geometry and global topology. It's actually rather similar to the Aharonov-Bohm phase I mentioned earlier. The Aharonov-Bohm phase is a global thing. It's not a local thing. Yeah.
Couldn't you take the same box you used for the torus?
In fact, there are derivations of this theorem using quantum mechanics. So, yeah.
Couldn't you take the same box you used to define the torus in order to make a sphere?
The same,
starting with the box?
no, because it's locally flat. Okay?
No, but I'm saying
So, well, actually, Euler's theorem tells you how to do it.
yeah,
So Euler's theorem, this number is 2, I think. Or 1 or something. Or minus 2. This is a non-zero number. Whereas if the geometry is flat, it's impossible for that number, because R would be 0. It's impossible for that number to be non-zero. So
I just think I'd see before taking that, and if you take the box and like two close ones, you squeeze them together like an envelope, you make a sphere.
you've got to bend it. Well, no way to do that without bending the surface. And that's what this Euler formula proves. It's just impossible to do some identification and turn this into a sphere. So what you can do is do something else like this. Okay, this is the Klein bottle. And so that's something which you can choose the metric to be flat, but it also has other funny things. It's not orientable, for example. It doesn't have two sides, it has one side.
The similar thing for a sphere is if you identify, rather than like identifying the vertical edges and the horizontal edges with each other, if you identify like the two edges meeting at each point with each other, and then you get a sphere. But to do that, you've got to pretty much cut it up and then like, you know,
Bend it. I think you have to bend it. You can't avoid bending it. Yeah. Okay. Right. So, we've nearly finished. Sorry, I was hoping to get a little further. But this is a natural stopping point. So I think let me stop. We can have a couple more questions. So I didn't get to geodesics, but I'll do those on Monday. Yeah.
So does that mean that the Riemann tensor vanishes in dimensions lower than 4?
No. The relationship is that the Riemann tensor is the fundamental thing. This is the measure of the curvature. I mean, there are many ways of deriving it. One way is the convergence of geodesics. So, in flat space, this was Euclid's axiom for geometry. One of the axioms of geometry, which, if something is an axiom, it means you can't prove it. Okay? It's not a plus, it's a minus. If I say something is an axiom, that means, whoops, I don't know how to prove it. It's just intuitive, okay? So Euclid's axiom was that two parallel lines would never meet. Okay, and that was taken as obvious, but unprovable. And then Riemann's insight is that if you think about geometry intrinsically, that's obviously not true, because if you think about a sphere, you take two great circles on a sphere. These are the straight lines on the sphere. The nearest thing to a straight line on a sphere is a great circle, and two of them meet in 2 points. So Euclid's axiom was wrong for this kind of geometry. So it had to be just dropped. But so the Riemann tensor measures the convergence or divergence of geodesics, okay? And one can derive it that way. But then the Ricci tensor is nothing but a contraction of this. So in fact, the way it emerges is the Riemann tensor is sort of naturally derived in this way, with one index up and one index down. And then the Ricci tensor is equal to R mu nu mu lambda, just a contraction of the first and third indices. And the Ricci scalar is just a contraction of these two, G nu lambda. So the Ricci tensor and Ricci scalar are just derived from this guy. So these are generally not the Riemann tensor. If the Riemann tensor is 0, then everything's 0. In fact, there is a theorem. If the Riemann tensor is 0, the space is flat. If the Riemann tensor is 0 everywhere, the space is flat. That is proven in Weinberg's book. Any other questions? Yeah.
For higher dimensions, do you still use the Riemann tensor, or do you use a higher?
No, there's nothing else.
And it still has 4 indices.
Pardon?
It still has 4 indices.
It always has 4 indices in any dimension. So yeah, 4 is where things reach their final complication. There's nothing else. Now, there's a very interesting question that in 4 dimension, what is the meaning of this guy or this guy? Okay, do you just have to always think about this, or can I think about this? And Einstein, this is to prefigure next week. Next week, we're going to write down Einstein field equations. These are the equations which give you G mu nu. And when Einstein understood this much about Riemannian geometry, he said, well, what are the field equations? They're R mu nu equals T mu nu. Okay, what else can it be? The curvature of space-time is the stress tensor. Now, the Riemann is totally wrong to match the stress tensor, but maybe the Ricci does. This was almost correct. Okay, he wrote it down. In fact, it's very funny to look at his original paper on GR, because he hadn't really learned enough Riemannian geometry. So the original paper is actually all wrong. Einstein said my greatest blunder was introduce the cosmological constant. He's quoted as saying that. It's quite a joke because, A, he never said it. George Gamow said it about him. But he made lots of blunders, okay? One of them is that his original field equations are completely wrong because he didn't understand Riemannian geometry. You look at the original paper on the field equations, the field equations include this formula, okay? He insisted that this G here is the determinant of the metric. In his original field equations, he forced the determinant of the metric to be 1, which is not a coordinate invariant statement. Okay, so then there was a big dispute with Hilbert, because Hilbert, of course, knew all this backwards. And Hilbert said, that doesn't make any sense. But Hilbert then there was a big battle to get the field equations, and mathematicians claim Hilbert did it first. This continues as a controversy until about 2000, when some historians of science looked at all the original correspondence and everything, and they ended up giving the credit to Einstein, not Hilbert. But anyway, this was the first attempt, and then he corrected it to this form, G mu nu R, and this is in 4 dimensions. So you can also make a symmetric tensor out of R and G mu nu, and it turned out this is the right form of the field equations. You know, then you could say, well, what good is this Riemann? It turns out that the Riemann tensor can be written in terms of the Ricci tensor and Ricci scalar. You see, you have this. You can write things like R. Actually, it's going to be mu rho nu lambda. Sorry, R. Actually, it is, what is it? G mu lambda. And you can also write things like G mu rho G mu lambda R. So if you have a 4-index tensor, you can relate it to other 4-index tensors, which are products of 2-index tensor. And the statement is the following, that if I take the Riemann tensor and I extract everything which can be written in terms of these things, what I'm left with is another tensor called the Weyl tensor. And the Weyl tensor measures gravitational radiation. So in a sense, gravity, the curvature of space-time, couples to matter. But there's another freedom in general relativity, which is I can have waves, just like in Maxwell's theory. I can have waves which have nothing to do with electric currents. And in gravity, I have these waves, which don't need, this can be 0 for those waves. But they still exist, and they're measured by something called a Weyl tensor. And really, you should think of curvature of space-time as being Riemann, but Riemann is partly Ricci and partly Weyl. We may do that later, I'm not sure. Any other questions, comments? Yeah?
I have a question, but I have a feeling it might get answered next week. But let me ask anyway.
Sure.
So we started by stating the equivalence principle about the metric.
Yes.
Then we end up doing something that was known in geometry a long time.
Yes.
Before Einstein.
Yes.
So I'm a bit confused about the motivation.
So, I mean, Einstein's insight was that it's bending of space-time that explains gravity. That was his instinct. So then he tried to learn the mathematics for the bending of space and time. Now, the mathematicians had studied the bending of space, curvature of space, for a long time, but they had no idea this was related to gravity. They just did it for its own interest. Okay? They were interested in spheres or saddles or toruses, just for their own interest. So this mathematics was kind of sitting there, waiting to be used. It's always true in mathematics. Most of mathematics is irrelevant to nature. You know, the mathematical world in general is just some intellectual mind game. But occasionally, physicists realize, I need that mathematics. And so Einstein learned it with a small difference. You see, Riemann was not interested in things which were locally Minkowski. Riemann would be interested in spaces which were what are called Riemannian, where the metric has 4 positive eigenvalues. So I said the metric has 1 negative and 3 positive. This is sometimes called pseudo-Riemannian. Nevertheless, all the math is exactly the same. Okay, so Einstein had to make this little tweak to Riemann mathematics in order to use it. But next week, we'll write down the Einstein field equations, which use these mathematical constructions, but they really give a lot of physics.
Okay, so we are sort of getting to the point where Einstein basically realized gravity is precisely geometry.
Yes. Yeah, Einstein realized gravity was geometry. So,
mathematicians were just interested in geometry for its own sake. They didn't care about the physics. Yeah.
Sorry, it's a stupid question.